Hi and welcome back to the lab. And today here on the bench we have a vintage Heathkit combo. So that is the model HW12, which is a 80 meter band monobander. And so that is a kind of new project. We have to restore this nice old unit, and that will definitely not happen in one episode. So we definitely have to do some more sessions on that project, simply because I have to discuss with the fellow radio friend how to approach this project and what we are really going to swap out, to change, and what we want to do finally to bring it back to life. So this radio is from 1961 or 63, not 100% sure, but that means finally it is approximately 60 years old, and that might be a nice project for all of you. So let's go right to the bench and let's, as I said, go step by step. Okay, and here's what we have. So as you can see here, that is our main unit, of course. So as I already said, it is the HW12, which is the 80 meter band version. And here this upper unit is not only the speaker as it looks like on the first glance. So here inside we have our power supply. And since that is a tube unit, we definitely need different voltages, and for the transmitter we need a higher voltage. So therefore we get 830 volt DC produced here in our power supply, as well as for the receive circuit 300 something. And of course we need to get our filament voltage produced as well, which is classically an AC voltage, 6.3 volt or so. And therefore what we really need to do first is make sure that our power supply will work as it should. And therefore we start our project here with our power supply, because we can't start here with our transceiver until our power supply is working perfectly. So therefore, let's go right into our project. Let's start with the power supply. And I believe that even the power supply will not be only one session, because with our first episode on this we start to check out if it works, and of course we have to check some old capacitors where I believe we have to swap out here and there an old and faulty capacitor. But anyways, let's go into it and let's check out what we have. Okay, so this unit is called SB600 from Heathkit, and that is originally only the speaker. So there is nothing mentioned from our power supply. And I do not really know if this switch here, this key switch or whatever it is, if that is original. So I don't know. We have to find out this, and here we have a headphone jack. But then when we turn it around, we easily can see that we have here our power supply, whereby this cable here is of course our speaker connector, and all the other things here are related definitely to our power supply. And here, so this is a connector to interconnect the power supply with our transceiver, and you already see that we definitely have different voltages here. So minus 130 filament, common, 12 volt ground, 6 volt filament, and that is the AC switch, because that is something very important. We cannot switch this power supply on for its own. Even we have here of course a switch, but you finally can only switch it on by switching on the transceiver itself, because both switches are in series, and therefore we have here our AC switch and AC common. So we need to check that. So I have to bridge this both pins to be able to fire this unit up, and to finally check how it works. So first let's take our power supply out, and then let's see how it looks like. So okay, so I've loosened here the nuts underneath, and I am trying to pull here our chassis out, but well, so there we have our first difficulty, because we have here this white wire which seems to go to the front panel, and that seems to be the key. And according to the wire which has been used here, so that is definitely nothing else than an audio speaker wire cable. So that is definitely not produced to use it for mains power. So I think the first I will cut it off. So even if this will be used in the future, and I don't know, by the way, if the key is still available. Anyways, I think what we really have to do to cut it off, and then afterwards we can decide with the owner how to go ahead with this switch here. So therefore, quick and easy, let's simply cut it off here, and then we can go ahead. Okay, so we have here a top view, and you see it is very, very dusty. I mean, no wonder after 60 years or so. So therefore, the first we do, we blow the dust off. But I will do it, of course, outside. I don't want to have all the dust here in the lab. And other than that, I'm still not sure if this key switch which we have here in is really done by Heathkit, so that it was planned. Even Heathkit always were kits. But anyways, if I go here, don't know if we can show it, but I mean, over this key switch we have running 230 volt AC, and well, really, I don't believe that that is wanted, because if you look a little more carefully here what we have, so this contact here is touching here our housing, and that is definitely not a good idea. So therefore, first of all, not sure if it is really Heathkit design, and secondly, we need to decide if that will be used in the future. So first, what we can check here on our speaker is if the rated resistor is given, and you see it is 7.6 ohm, and according to the Heathkit manual, it is telling 8 ohm. And we all know that it is not a real resistor, because it is more an impedance, and it is frequency dependent, so the impedance change over you know, the frequency, the audio frequency. But we can check it with the ohm meter, and there we normally see the rated resistor for the speaker, and that looks quite okay. But let's check here our speaker at our generator. So I am feeding in 30 millivolt RMS, and okay, so we can hear it. I increase the level just a little bit, and yeah, to me it definitely sounds good. So we can change a little bit the frequency as well. Let's see what we can do here. Okay, so let's go from here. Yeah, so that is definitely good, and we can put our speaker aside and go ahead with our power supply. Okay, so we have here our power supply, and as you can see, I have cleaned it a little bit. Looks much better now. So we have to take off here our bottom plate to get access to our circuit, and other than that, we have here our net transformer, and that must be here a choke to eliminate the rest from yeah, the 50 or 60 hertz hum, to have a very clean DC, at least for our circuit. But anyways, let's yeah, and of course this here are capacitors. Let me see if we can read it. 450 volt DC and 125 microfarad, I believe. I'm really curious if these capacitors still are working, or if they already are leaking, so we will find it out. But now the first will be to take off here our lid or button plate or whatever. Okay, and here is our circuit from underneath, and as you easily can see, it is tube or valve free, so we definitely have already diodes here. So that seems to be silicium diodes, but we will double check that as well. You see here another bunch of capacitors. So that are the old paper or wax electrolytics, which I'm really curious how good they are. And well, considering that this is a kit which has most likely built from a radiometer, I think it is not too bad in its craftsmanship. So looks quite nice. Maybe here and there minor comments I could make, but no, in general it is very, very nice. And what we can see here as well, that has definitely made afterwards, so that needs to be either with a proper wiring, but I do not really think that a key lock switch is needed. But anyways, have to discuss that. Other than that, normally it is a 120 volt version, so that seems to be the European version. Even I'm not entirely sure. So we have here, of course, an European wall plug, but it could be that it is already replaced. I really do not know. It all looks a little bit not original to me, because 60 years ago wall plugs looked different to what we see here, and that really makes me wonder if it is really a 220 volt version, or is it maybe a 110 volt version, and nobody really knows that it is 110 volt, connected an European plug to it, plugged it into the wall, and then suddenly the magic smoke came up. Because if that here is only the 120 volt version, then of course 220 or 230 volt would have killed it. But that is something we definitely can check first. Okay, to do a quick check on our primary side of our transformer, I have here connected this wire here to our circuit breaker. Then it comes out the circuit breaker, goes here over our switch, finally over this black wire from the switch, as you may see, to our connector. And that is what I've told you before. So our connector here is in series with our connector here. So only if we have connected our transceiver via this cable here, right, we can finally switch in our power supply. So therefore we have to, oops, not so fast. So therefore we have to connect here a bridge wire from the black here, this one, over to which is going to normally to the transceiver. And now we get a reading of 5 ohm on the primary side for the 230 volt version or 240 volt version anyways of our transformer. So that is already a good news. So it seems that it is not burned, or no, not it seems, it is not burned off. and I hope still that it is a European version, because it could be, in worst case, that somebody puts a new volt plug here to the unit and never tested it for, I don't know, any reason. So therefore, still try to find a hint if that here is the right transformer. Okay, so looking here at our 240 volt wiring, so we see the black wire out of our transformer, and the black and yellow get bridged by the black and green, or with other word, black and yellow and black and green wire get bridged, and then we have black and red, and that is then finally our 240 volt connection. Here on our board here, so we see that we have here our black wire, okay, and the black wire is then here connected with the black yellow, which is the second end of our first winding, and then the green black, which is our second winding, which is here switched together. Hope you can see that. And then the other end of that construction is our, you can see it here, I hope, our black and red, which is going up here to our connector, and that is the one which is in series with our second switch here, or first switch, whatever you want to call it. So that means that it is definitely wired as a 240 volt unit, and that means it makes sense that it is not burned off our transformer, so everything is fine and it should work. Okay, so that is now clear. Next is, of course, before we do a first test run, and well, we do not simply plug it in our 240 volt main plug, so we do it very carefully over our insulation transformer, which we can adjust in voltage, and of course over protective light bulbs. But first we can do a quick check on the ESR if we see something unusual on our 1, 2, 3, 4, 5, 6 main caps here, to have a first feeling. Okay, so I've performed a quick check here on the electrolytic capacitors. So the ESR, of course, and it is really impressive good. So all capacitors seems to be ESR wise fine, and so on the other hand, DC ohm tests are fine as well, so that all is definitely good. I think we can perform a live test very carefully and see how it performs. But I think we should bridge here this both wires over really a wire, a soldered wire, to be sure that that is solid and cannot make any shorts or such. So let me do that first and then we go ahead. Okay, so what have I done? I have connected back here our mains wire, mains cable, that we really can feed here our power supply. And I have tacked here, really just only tacked this bridge, that we really do not forget to put it off afterwards, so that we do not create here a short. Well, other than that, yeah, let's see how the old capacitors turns out. And well, we're gonna increase our voltage very, very slowly, and watch, of course, here our safety bulbs, which will finally limit our current through our unit. And okay, we see up there what the current is, which will be drawn by our unit, and that all together will give us a first impression on what we have. Okay, so everything is prepared. So I'm gonna start to crank up the voltage which will be finally available at our power supply, will be displayed over there, and of course on our instruments, on our safety transformer for sure. Then it runs here through our light bulbs, and they are connected in series, so they are a current limiter. If we see that they start up flickering, then we know that something is funny, and I directly reduce our power supply, our transformer. That's what I mean. So then we see, of course, here the amps, which will be drawn by our power supply, but that should not be so much because it is unloaded. It is running free, so without any load. So therefore it should be very limited, except there is somehow a short, because what we have not done is checking finally our capacitor leakage. So that is something we don't know. We only know that our ESR is not horrible wrong. Okay, so let's try and let's see how it works out. So you see it is going up here. And by the way, I have set our transformer to 250 volt. So we have the switch, you remember. So looks all good so far. So we are drawing here 50 milliamps. Okay. No problem so far. So I do not see anything here with our bulbs, which is definitely good. So all is normal. Very good. But already 20 watts, 140 milliamps. I do not really know where this is going to. Once again, it is without any load, and we have 140 milliamps, which is, well, it is not dramatically much, but for power supply, and once again, it is not a tube power supply, so 30 watts without any load. Okay. We are already at 207 and we go up to 230 and 40 watt or almost 130 is fine. To be honest, 40 watt almost 230 milliamps without any load is somewhat, yeah, abnormal. Let me call it that way. Let's go over to our circuit. Okay, according to our circuit, we see that we have here bleeding resistors for, yeah, finally discharging here our load or our charge finally. So these capacitors are 450 volt as we have seen it, and well, we have only 100 ohm in parallel, which are then, or is it a K? Is it K or is it R? I cannot really read it because 100 air would be a little bit too low, so therefore I believe it is 100K, which makes much more sense, and that as well should be 100K. And here, yeah, what is that? Okay, that is bias adjustment. Okay, that is a 10K pot. Well, still, that means 40 watt for nothing is still a little bit too much in my opinion. So that could mean that we have a component which is leaking, which would not make me wonder, because, you know, as we already discussed, it is 60 years old. Okay, I think with our bulbs here in series with our power supply, we can risk to check the voltages. Still, we have, from my point of view, a much too high current flow, which is not really normal, since there is no load or no internal loads which really can cause such a high current. So therefore I think we can risk to finally try to check out the voltages which are present here at our socket, and see if the voltages are reaching the rated values. If not, that is definitely another indication that something is leaking. I mean, something is leaking, even we cannot directly find it. Also, still our capacitors are yeah, a kind of the main point where it can happen. Anyways, let's again crank up here our system to, let me say, 240 volt, simply because it is rated for 240 volt, and that's the reason why we crank it up until that is a bit too much, but 35, nah, let me do it without the camera. Okay, 240, 26 watt and 230 milliamps, which is quite a lot. So that is now what we have here at our power supply. And maybe that our power supply is not our power supply, our capacitors are getting reformed so that they are getting better. But anyways, let us check. So here we should see minus 130, and we have minus 124, which still could be. Next one is plus LF, so that should be either 273 or 350. We have set it here to 300, and what I've already seen before also, it is switched off. We still have here, it is always a little bit difficult here to get the contacts. No, I'm not able. Or is it now switching? Because I have recognized that it was not switching. Well, let's see. No. Now there is definitely nothing. That's funny. That is funny. I cannot read anything. Once again, can I read my minus? Yes, I can. What's about our H V here, high voltage? I have 772, so that is the voltage for our transmitter. It should be 830, no, or 820, I believe, as far I can read it here. So that would be too less. And once again, why I am not able to read, okay, 260, which would be okay. Now let me switch it to off once again, which would be okay, and that should be minimum 300. Okay, once again, nothing. That is somewhat funny. So still something is definitely not good. So maybe that for some reason, 260 or is present, but when I switch it over here, there is nothing. And the question is, why is it so? I don't know. That is funny. So of course we need to check that. 260, which is fine, but still 773 volt is definitely too low. Yeah, so that means that something is loading here as a power supply, that it is not finally able to give out the right voltage without any load. Okay, so let's summarize. We have some weird issues which we need to identify that we really can go ahead. So first of all, we recognize that we are missing here the 300 volt DC, whereby the 250 we have. Then we have recognized that we have a kind of load where we not know where it is coming from. A short check of our capacitors were, yeah, let me say, were not bad. So we tested the ESR and we did not find something special, but that still could mean that you know, their that capacitors are leaking, so that would explain the load. And then we found, when we tested here the high voltage, which should be 820 volt, we measured 770 something, which is definitely too low and indicates a load. And when we look here at the specs we have from Heathkit, so we see output voltage here should be 820, so that is what we were looking for, with no load. Okay, and that is important because with 700 or with a load of 250 milliamps, we have 700 volt DC. So that is simply because this voltage is not regulated. So that is fine, no problem. But we should see 820, but we don't. We see 50, what is it? 50 volt lower, which indicates what we have seen and guessed before, that there is a toxic load, and we need to identify where it is. And then the second odd thing was that you know, we were only able to get 260 volt, but with this toggle switch we should get 300 volt. And there I found that obviously it is wired wrong. So what we have here is a toggle switch in 2 layers. I don't know, yeah, so you should be able to see it. So normally the middle position gets whatever is fed here to this switch, and then we can switch left and right and bring whatever we put here into the middle to one or the other side. Okay, and that of course makes sense when we look here at our schematic. So let's see how we can see it best. So first of all, this switch here, oh no, on this set is funny. So that is the US version. So hang on a second, we need to go over to the European version, and here it is definitely more clear. So let me enlarge it here a little bit more, and well, let's see here our switch. So we see here our toggle switch, and you see when we're talking about our power plug, you see wherever the toggle switch is switched to, we always switch, if you like, our power supply on. So that is one layer. The second layer is here, but let's again watch what I said before. So in series we find here, oh, you can't see it, sorry. In series you can find here our AC switch at our connector, which we have bridged so far because we do not have our transceiver connected. So you see that is a toggle function on the net side on our supply, net supply voltage, if you like. And then we have the second layer of our toggle switch, and that is our switching between 250 and 300 volt DC, and that is what you see here. So in the middle, of course, it is switched off. If we switch it to brown yellow of this part or portion of our transformer, then we get our 250, and when we switch it up here to the brown wire, then we are using here the whole coil, and that means we expect 300 volt. And that is not working simply because that is wrongly wired at our toggle switch. And you can see it here a little bit. So here's our brown and that is a brown yellow, sorry. And here is our brown wire. So that is the switching between 250 and 300. And you see here in the middle where we should have connected our C3, which is a capacitor down here, okay? And this wire here should be here in the middle, so we cannot really switch between these both voltages. So that is wrong, and I hope that there is not a fault somehow, that it has changed some times ago, because there was a malfunction, so we don't know that yet. And you see that we have here the second layer, so that is the main switching, is it is also wrong, definitely wrong, and it needed to get done better or new. So yeah, that is definitely a problem we have here. Anyways, we have to rewire it in any case. And then additional to that, I found another problem. Let's see if I can focus on that. Let me see. And if you see this connector here, you see it was never soldered. Yeah, you see it is really open, so that was never soldered. So that is our bias adjustment, and I really wonder if it ever was working properly, because simply if it is not connected, it does not really work. Okay, so you see there are definitely more than only one problem, and that is what we always have with Heathkit, with Heathkit kits, because a lot of things can go wrong, and I've often seen Heathkit kits which where the production was not good, and so we found malfunctions and so forth and so forth. So that is what we here have as well. So it is wrongly built, and you see this here is also wrong. So this diode should not be attached here to the capacitor, so that is definitely wrong. So that needs to get fixed as well. Yeah, and other than that, maybe there is something what I have not found yet, but I really do not see another chance than to take it apart, that I really get down to our capacitors to be able to perform a leakage test with or on the rated voltages, and therefore we have to disconnect, of course, the wires, because if I apply 450 volt to the capacitors here, and we found that here that these are 450 volt DC capacitors. Oh, by the way, so I haven't shown that. So that is only a sleeve which is over the original can, but that makes no difference in general. But when I apply 450 volt DC to each of the capacitors to test for leakage, then of course I have to disconnect the rest circuit to be sure that nothing else get damaged. And of course we need to check these capacitors as well. I mean, the big one here is a 450 volt version as well. These both little ones are 150 volt DC, and I need to check this old carbon resistors, because they are known for running out of tolerance, even what was silver, 20% tolerance, I believe, if I'm not totally wrong. So today a silver tolerance ring is not seen so often anymore, because it is today much easier to produce in a better tolerance, let me call it that way. And yeah, so next steps is to get out here our switch, to get under it, to get access to the capacitors, and then we check the capacitors, and then we decide how we go ahead. Okay, so I have ripped it apart a little bit, and it looks a little bit disturbing, but finally it is the only way to get to the capacitors, to get really clarity where we might have our load, which I believe is a kind of leakage current through our capacitors. So now we can really go around, check each of our 125 microfarad capacitor with 450 volt DC. So let's go and get started. Alright, so our first capacitor value 151, which is bad as it is over 20%, but okay. Our ESR is good, 0.23 ohm, so that is still good. Dielectric Observation is, let me check that, 30%. That is bad, definitely not good. Okay, and let me check the leakage finally. Oh, 15, 10 milliamps, 9 milliamps, bad. Yeah, so that is the first capacitor which is not able to really hold the current flow small. So that capacitor is already leaking, and definitely it has to go. So now let me go over to the next capacitor, and I'm back in a second. Right, the first one which we have tested was just for our protocol was the C2. Now the second one is the C4, where the test leads are connected to. So let's go. Value, well, 153 bad, but well, that is not that dramatic. ESR 0.34, which is still okay. Dielectric observation is 6%, not as bad as our first one. Anyways, let's check the leakage. Oh, it just jumps off. 1 second. My test lead jumps off once again. Capacitor leakage. Oh wow, 18 milliamps. It is dropping, but too slow, and still 13 milliamps, where it should be somewhere in the microamps, which is definitely not good. Let me go check again on the dielectric observation. It is not possible, because still there is a lot of load in the capacitor, which is, you know, what is not good, because this dielectric observation is, if you like, the rest voltage which builds up after this discharged. And when we have discharged here, or when we have tested for capacitor leakage, then of course if I release here the button, it gets discharged, and so we shouldn't have left any voltage on our capacitor, but this is now telling me that I cannot test it, because there is definitely too much load on the capacitor, and that is a clear indication for that something is horrible wrong. And I mean, we see it when we test for leakage. So that is the load we have seen all the time, right? Okay, let me go over to the next one. The next one I'm testing is C3, and it is same values. So we start once again with a value 164, so that is even higher, which is bad. Then let's go over to ESR. What is it? 17, which is good, definitely. Let's see what we have here. I mean, the capacitor 12% is totally discharged, right? So I have done it manually, and so we are able to test this value. Now let's charge it, and let's see the behavior. And you see that is even worse. So you see it is blinking here, 88%, 88 milliamps, and it is blinking. So this capacitor is totally toasted. So it is not a DC block any longer. So this capacitor became finally a resistor. So now you see that my assumption was right, that the load we have seen with the very first test on my power analyzer was right. So the load, what we have seen, is the faulty capacitors. Okay, let's go over to the last one from our stand-up capacitors and let's see what we have there. Okay, and that is now the C1 which I have connected, and let's do exactly the same. 168 microfarad, bad. Now ESR, which still looks good, 0.25, no problem. Our dielectric observation is 6, which is good. Remember, it is totally discharged. And now let's go to capacitor leakage. And this is 13, 12. It is going down, but anyways, it is bad. And you see, 10 milliamps is really much too high, where it should be somewhere in the microamps. Let's see now if I'm able to test for dielectric observation. No. And that is exactly what I have expected. Now there is building up a load after we have discharged it, and that is a problem with those capacitors as well. Well, so we have definitely 4 capacitors which has to go. But of course we have here another 4 capacitors which we need to check as well. So let's go over, and then you have finally the whole story, what's going wrong here with our power supply. Now we are testing the C5, which is a 40 microfarad and also 450 volt. So let's see. 53, it's a bit too high. ESR 1.15 is still good. Dielectric observation is with a total discharged 7% is good. And now let's see what our leakage is. 18, 13, and that again is bad. And you see it, the bad signal or sign comes up, and it is not dropping enough that we can expect to get it down to into the microamps, so that capacitor is dead as well. Now our last both 20 microfarad and 150 volt capacitors, so let's check. 22, which is good. ESR 0.54, well, okay. Dielectric observation will be good, I believe, as well. Yes, and now the leakage, which is too high. Oh, it's coming down. So, no, wow. So that was definitely fast enough, and you see it is dropping. So that means our 20 microfarad capacitors are still good. Nice, really. So you see it's going down 65 microamps. That is fine. So let me connect meanwhile the second one, and let's see what we get there. So it looks like that we really have 2 which are still fine. Yes, 23 is good. ESR is good. The dielectric observation is good. And now capacitor leakage, 3 milliamps, and that is dropping. Great. Look at this. So these both capacitors are still good, Yeah, that was not expected. Great. And finally, we have a result. All our 4 capacitors here, so the stand-up ones, are definitely dead. Here our 450-40 megahertz as well. These both are good. So really good. But anyways, I just wanted to prove that these old capacitors are most of the time leakage. So normally I would have swapped them out because it is clear a 60-year-old capacitor is always a problem. And you see that these 4 capacitors were the ones which was creating finally our load to a not loaded power supply. And of course we are gonna swap this as well. I mean, I hope. I now have to stop here, and I have to discuss, of course, with the owner what he wants me to do. So maybe, I don't know, he may say, oh, that oil becomes already much too expensive. So already here our caps are not really cheap. So I mean, these caps are not that cheap, not that expensive, but these caps down here are expensive. And well, so we have to discuss it. We stop it now, and yeah, stay tuned for the next episode on Heathkit. I mean, it will definitely take a little while, but definitely we will go ahead, and let's see what we can make for a progress. But for the moment, we stop, and I have to say bye, and catch you next time.